It gives me great pleasure to welcome you all for today's lecture. It's a special lecture, as you know, by Professor Biman Nath. He is from the Raman Research Institute, and he obtained his PhD from Maryland, working on various aspects of diffuse matter in the universe, mainly the physical processes responsible, say, for ionization, for enrichment of heavy elements and the like. Currently, his area of interest is the galaxy ecosystems, which means interaction between galaxies and the surrounding material. He has been also working on the supernova remnants. It's also important to know that he has taken keen interest in popularization of astronomy science, which fetched him an award from the Indian National Science Academy. His interest in the history of astronomy has resulted in very interesting books. Maybe you have read some of them. The Story of Helium, Dawn of the Universe, Eyes on the Sky, and he has written several more in Bengali. He has authored several books which are classified into fiction. Nothing is Blue is one of them, and maybe some of you have read the book. It was nominated for the Vodafone Crossword Book Award. The other is titled The Tattooed Fakir. Now, it's a great pleasure with which I am welcoming him here for this thing. And we are thankful to you for having spared your time for this lecture. We now look forward to a very interesting lecture. Thank you.
Thank you, Dr. Shailaja, for having me here and for this asking me to give this special lecture. And good evening to everybody. Thanks for coming. Do I need to speak to this? I don't need to, right? Okay. So I'm going to talk about our stars in our neighborhood. I know that it's not a topic that makes headline news. It's not an exotic topic like the beginning or the end of the universe, or galaxies at the edge of the universe, or extraterrestrial intelligence, or remotely as exotic as that. However, I would like to tell you some interesting things about the stars in our vicinity, the stars that we see almost every night. We tend to ignore the locality of our galaxy where we are situated in, thinking that the stories of these stars may not be very interesting. After all, our star, the sun, is a very average star in many respects. Its mass is average. It's not too low, not too high a mass among the stars. And its temperature is also somewhere in the middle, which is why its color is yellow and not, which is in the middle of the rainbow spectrum of blue to red. So the blue stars are very hot and red stars are cooler relatively, and yellow stars are in the middle. So sun is, the temperature is also somewhere in the middle. It also happens to be a middle-aged star, halfway through the estimated lifespan of about 10 billion years. So it's a run-of-the-mill star, and you don't expect many interesting stories about stars like that. And we think that in our neighborhood is also a mediocre region in the outskirts, quiet suburb of our galaxy, away from the hubbub of the center of the Milky Way. Now, it's true we don't live in the most exciting parts of the cosmos, but what I would like to tell you in the next half an hour or 45 minutes or so, that there are this neighborhood also, this region also has been witness to many interesting events related to the evolution of stars. So there are, in the neighborhood of our neighborhood, there are associations of stars, very young stars, from which are, and then there are very dense molecular clouds in which you can see young stars being born. There are wisps of clouds which are nothing but ashes from explosions which happen at the end of the life of a star. Then there is also a freak object in our neighborhood, which probably originated in one such stellar explosions. I would like to talk about some the supernova explosions in our vicinity, from which probably the debris even fell on the Earth, and it's possible that it changed the history of the evolution of our species. So, but before I go any further, I should like to define some of the length scales involved, and I should like to define what I mean by the neighborhood. So, what I have in mind, a region of about 500 light years across, okay? And I would like to put this in the perspective of our known world, solar system and our galaxy. So, in our solar system, you know that the Earth is about 8.5 minutes away from 8.5 light minutes away from the Sun, which means this light takes 8.5 minutes to reach from the Sun to the Earth, and that's a useful, a convenient unit of distance in terms of how long the light takes. And our solar system is about a few light hours. So, Neptune is about 4 light hours from the Sun. So, that gives you an idea how big it is. And if we zoom further away, then we would have to go a few light years before we reached the nearest star. Conversely, so let me show it here. So, this is it a pointer? Is that a pointer? So, this I am going to slowly zoom away from the solar system. So, that is the inner planets, the Mars, Earth, Venus and Mercury, and then we zoom further away. So, this size gives the size of the box which contains these pictures. So, when you go to 10 billion kilometers, you would see this is a old slide which has the orbit of the Plutos, but Pluto is not a planet anymore, considered a planet anymore. But this is Neptune. So, this is about 4 light hours away from the Sun, and then we can zoom away, and if we go to a few light years, then we would see the nearest star. That is the typical distance between the stars. And if we keep zooming away, we will see our Milky Way, our galaxy. So, this is the Milky Way, our galaxy, which is a spiral galaxy. So, let me see it, our position from the vantage point, from the point of view of our galaxy. So, as you would know, Milky Way is a typical spiral galaxy, which means there are many spiral arms coming out from the central region. And our solar system, we are basically inhabiting one of the arms, which is called the Orion arm, the name of which will be clear as we go along. So, these are different arms in the solar system. Our solar system, the Milky Way is about 30,000 light years in radius. Okay. So, this is 30,000 light years in radius. So, there is one reason why I would like to talk about the neighbourhood stars, because these are the stars that we see every night with our naked eye. So, if you look up in the starry sky at night, the stars that we see are not very distant stars. There is a large amount of cosmic dust in space which obscures our view, and so we do not get to see stars which are very far. So, this is typical. So, this is the Milky Way, and these are the stars that we see with the naked eye. Red stars are marked blue on orange, and blue stars are marked blue. And as you can see, these are the stars that we see with our naked eye, and they are basically localized in a region of about, say, 1,000 light years or so. We do not get to see stars beyond that. So, our view of our Milky Way from our vantage point is quite limited. So, let us first explore the region of about, say, 50 light years around us. And if we could observe this region from a distance, what we would find, we would see a few bright stars. So, for example, we would see Altair, which is around 50 light years from us, which you can see in the summer sky. So, Altair, you can see those who know the sky, in the summer sky there is a summer triangle you can see formed by 3 bright stars, Altair, Deneb and Vega. It is a summer triangle. It is a very prominent star, and Altair is known in Sanskrit Shravana, right? So, that is related to the month of Shravan, I think. So, in that month you will see Altair rising in evening, right? On the other side of the Earth, so this is Altair, it's about 50 light years, and on the other side of the Earth, which means it will be a winter sky with the stars which would show up in winter sky, we would see Sirius, which is the brightest star in our sky. Sirius is about 9 light years away from us, and we also see Alpha Centauri, Procyon, that's also a bright star. But what is also interesting is not just the bright stars, but what lies between the stars. And if we could explore this region, we would see that our sun is immersed in a bath of very hot and tenuous gas. Let me see if I can. So this was Sirius, and you can see Sirius is close to the Orion constellation. Okay, so if we could explore, if we could zoom out further, we would see that our sun is immersed. This is our sun, and there is a bit of hot gas around us. This region is further surrounded by a region of very light gas, very lightly dense, very tenuous gas, very hot gas, of a region of about 500 light years, which is further surrounded by a region of very hot dense gas. So this is dense gas. Okay. So this region of about 500 light years across is known as the local bubble, and the gas, slightly denser gas, which is blowing towards our sun and the solar system, is called the local fluff. So this is the region I want to talk about, 500 light years across. Now I would like to give an idea of the density that I'm talking about when I say how dense or light these gas are. So you would know that the density of the air in our atmosphere on Earth is about 10 to the 19 molecules per cubic centimeter, right? How do you know this? We know that 1 mole of every element contains the Avogadro number, 6 times 10 to the 23 number of molecules, and under standard pressure, temperature, you would know how each mole of each element would, what is the volume that they would occupy. So from that you can find out that the density of air on Earth is about 10 to the 19 molecules per cubic centimeter. Compared to this, the average density of the gas in our Milky Way is about 1 atom per cubic centimeter. There's 1 atom per cubic centimeter. So cubic centimeter is a volume like this, centimeter all the way, and it's just 1 atom. So which is very, very empty. It is more empty than the best possible vacuum that you can have in laboratory on Earth. Okay, and the gas in the local bubble that I'm talking about is even further lighter than this. It's about 100 or 1000 times lighter than the average galactic average of 1 atom per cubic centimeter. The gas in the local fluff is slightly dense, but still. So that gives you an idea of how, when I say dense gas, it is how dense it is. Okay, but before we talk about the origin of this gas in the local fluff or local bubble, I should remind you that the sun is not really at rest or stationary with respect to this its neighborhood. All the stars have random motions. Now you know that stars in our galaxy, they are all revolving around the Milky Way. So the sun and its neighborhood, it's going around the Milky Way at a speed, with a speed of about 220 km per second. That's a huge speed, 220 km per second. So the sun, there's a relative speed between the sun and its neighborhood stars, and on average that's relative speed is about 20 km per second. 20 km per second. Okay. So given now that I've given the size of about 500 light years and the typical relative speed of 20 km per second, then you can estimate the time that sun is going to take to cross this local bubble. And you can just divide the total distance divided by the speed, and you'll get a time scale of about 7 to 8 million years, roughly. So that's a very short time compared to the astronomical time scales of, say, the lifetime of the Earth, which is 4.65 billion years. So, so the 5 to 10 million is a very short time. All right, that's the time. So we have been basically going through this local bubble in the last 5 to 10 million years or so. And astronomers think that this region has been important for us to have been shielded by this dense gas around this local bubble, which has shielded us from the harmful radiations which are coming out from different other parts of the Milky Way, more exciting parts of the Milky Way, for example, the center of the Milky Way, where there is a monstrous black hole, and there are harmful gamma rays, UV rays coming out from this region. And this region, we have been shielded for the last 5-10 million years. And you know how important last 10 million years have been for the evolution of our species, right? So, as you can already see that there is a connection between our neighborhood and what happens on the earth. And so, you know, we are probably living in a very mediocre region of a galaxy, but it's not very irrelevant. Okay, so, so where is this hot gas that the local fluff that I showed, where is that coming from? So, let me show you the pictures again. So, this is the local fluff, this hot gas is blowing around the solar system. Now, it appears that it is coming from a nearby association of stars, the Centaurus, Scorpius Centaurus association of stars, of young stars. And so, this is a schematic diagram of our neighborhood again. So, this is the sun, and you can see the hot gas, the local fluff coming, and it's basically coming from a nearby association of stars called the Scorpius Centaurus association. There is a large molecular cloud near us, whose name is Aquila Rift. Now, I should explain some of these words that I have used: molecular cloud, association of stars, and we should try to also understand why there is an association of stars near a molecular cloud. To understand that, we should understand how are stars born. So, stars, as you know, I'll come back to this. Stars is, so maybe I'll just show you the picture of, so this is the Scorpius Centaurus association, which basically means this is association of stars in the direction of the constellation of Scorpius and Centaurus. Okay, Scorpius, I mean Scorpion, as some of you may know the constellation of Scorpion. If you look up these days at midnight, I think it's overhead. And there is a reason to see Scorpion these days because Saturn is pretty close to Antares now. And it's a very interesting looking constellation because it actually looks like a scorpion. Okay, and this is the red star, Antares star, at the head of the scorpion. You can see the tail, very beautiful tail. So that's in that direction there is this association of star, and there are some young stars in that region, and from which the hot gas is blowing towards us. So I wanted to understand why are there molecular clouds, what I mean by young stars, and why should young stars be blowing winds like this. So to understand that, we should understand how are stars born. So stars, as you know, are nothing but fiery balls of gas in which the temperature in the center is so high that there are thermonuclear reactions going on there, which makes the stars shine. So, for example, so this basically sun, all the stars, there is a balance between the gravitational force which is trying to contract and the pressure due to the energy production in the core, okay, and that keeps the gas in some sort of a balance, in some sort of an equilibrium, and that's the stable phase of stars. So in the sun, for example, what's happening? 4 protons combine in the center to form one helium nuclei, and a tiny part of this mass is converted into energy by this famous formula, E is equal to mc square, in the form of radiation, which makes the stars shine, makes the sun shine, for example, and that takes a minimum temperature of 10 million degrees. So the core temperature of our sun is about 15 million degrees. Now that's easy to achieve. So if you want to give birth to a star, you have to have a situation where the core temperature is very, very high. Now that's easy if you have a huge mass, because the gravity is going to provide the pressure, and you know if you put pressure on the gas from high school physics, it's going to become hot, right? But why should a free floating cloud in the interstellar space should suddenly start collapsing and form a star? If there is a cloud in interstellar space, right, it's for some reason, suppose it starts contracting, it will become hot and then it will resist its contraction. It's very difficult to make a star, a ball of gas, to contract all the way and make it very hot, right? And that can only happen if you can somehow keep the gas cool. As it is, as you contract, it becomes hot, but you cool it, then let it contract further, cool it further, and so it will keep contracting, and so you have to let it cool somehow, let it radiate away energy, and in that it turns out molecules are very important. If this gas has a lot of molecules, then it's easy for the gas to cool, and so it can contract and to the extent that it can become very hot. That's why the presence of molecules are very important for forming stars. Now there are dense clouds in our galaxy which are very dense and very cool in the sense of say 50 to 100 Kelvin, which is say about 100 and 150 degree below the 0 degree, right? 273 Kelvin is 0 degree centigrade. So I'm talking about negative temperatures in the centigrade scale. And so these are very dense gas, very cool gas, and they have a lot of molecules. And the conditions for formation of stars arise in these clouds. And then the clouds which are very big, we call them giant molecular clouds. And one local example of such giant molecular cloud is the Orion cloud. I'm sure people have seen the Orion constellation, and as you know that, so this is the Orion belt, and this is the sword of Orion, right? So there are 3 stars which delineate the sword, and the middle star, it's not really a star. If you point your telescope towards this star, you'll see this fuzzy gas, and it's basically Orion nebula, and you can see with a powerful telescope we can see young stars being born there. Now this region is a portion of a huge molecular cloud which we cannot see normally because it's so cold that it doesn't radiate. You can see only through infrared telescopes. So this is an infrared image of the same region of the sky which is otherwise black, but in infrared telescope it shows up as a huge region. Also in radio telescope we can see that. So these molecular clouds have portions in which star formation can happen, and so in these portions what happens, there are fragments which in which all these cloudlets are going to form individual stars. So whenever you see a molecular cloud, and it's likely to have a star forming region around it, and star formation happens in multitude. For example, all stars are clustered. So you are likely to see an association of stars. Now a very interesting thing is, so for example, this is you can see association. It is a molecular cloud and young stars which are burning away the molecular cloud. Now one interesting thing about stars is that massive stars radiate away, they lose energy at a much bigger rate than low mass stars. It's like rich people, they spend a lot, right? So the massive stars are likely to run out of their fuel much earlier than low mass stars. Okay, so for example, sun, with the rate that it is losing energy now, the way it is shining now, it's going to shine for about more than say 5 billion years more, and it has already lived for 5 billion years. We know that the Earth is about 5 billion years old, 4.65. But if you take a star which is 10 times massive than the sun, 10 times more mass, then it's going to run out of its fuel within a few million years, not billions, million years. So massive stars, they live shorter, okay? They die young. So whenever you see a very massive star, it is likely to be a young star because it must have been just born, because their lifespan is very short. So when you say young star, it's likely to be a massive star, right? And massive stars are hot because of their gravity, so they are blue, right? And another interesting thing is the massive stars is that because they are very bright, because they are losing energy at a very large rate, the pressure of the radiation can throw away the gas from their outer surface at a huge speed. So, massive stars have large stellar wind. Our sun also has some kind of a solar wind, and you know the effect we can see, we can feel the effect of this solar wind on Earth because we see aurora borealis, etc., etc. But massive stars, the stellar wind from massive stars, this is an example of Antares, which is a massive star, can be very effective, enormous wind coming from these young stars. So, that is what I meant by young stars in the association of Scorpius Centaurus, and the wind from those stars are basically blowing towards the solar system and creating the local fluff of gas. Now what happens when stars run out of their fuel? Basically, the possibilities are, there are two possibilities. If the star is say less than 10 solar mass, then what happens? It runs out of the hydrogen in its core. So, for example, the sun right now it's burning its hydrogen to form helium, and after 5 billion years it's going to run out of its hydrogen fuel in its center. Then it's going to start burning hydrogen in right outside the core in a shell, which would basically puff up the star, make the star very expand, very large, and which will cool this outer surface of the star. Now that happens for a region it's slightly involved that I can't really explain in a short brief span of time. So ultimately the star is going to become very large and slightly cool the outer surface. So it is going to look red and it's huge. So we call them red giant stars. So one example, so this is an artist's conception of how sun is going to look like 5 billion years from now as a red giant, and is going to loom very large on Earth. Earth, as we know, is not going to look the same because there is not going to be any life, because it is going to be so hot at that time. One local example is the Aldebaran star. Aldebaran is a star which is in the head of the Taurus constellation, and in Sanskrit it is known as Rohini. It's a giant star. It's not very massive. It's about 1.7 times the mass of the sun, but the size is about, I think, 65 times 45 times the size of the sun, and it's red because it's cooled, and so it's a red giant star. Another example, so this is the Taurus constellation, and you can see Aldebaran there in one of the eyes of the bull is Aldebaran. Arcturus is another red giant star. This is in the constellation of Bootes. It has a similar mass that compared to our sun, and the size right now is about 25 times the size of the sun. So it has not really expanded like Aldebaran. So it has not cooled and become red. It's a sort of orange star, right? So it is. So for example, red giant star. So this is Arcturus, and compared to this, the size of the sun is very, very small, right? So what happens at the end of this red giant phase? When the star becomes very big, it loses the outer surface because the gravity has become very weak, and finds it very difficult to hold on to its outer surface, and the gas is lost, and this phase we call it a planetary nebula. And the core of this star becomes shrinks because there is no energy generation anymore, because it has run out of its hydrogen fuel, and when there is no energy generation, gravity basically wins. The life of a star is basically the story of balancing gravity with some sort of energy production, so which gives it some pressure, right? Once the energy generation stops, gravity wins, it shrinks, right? And it becomes what we call a white dwarf star. White dwarf stars, for example, the mass is going to be similar to that of sun, but the size is going to be very small compared to like that of the Earth, for example. So the density is going to be very, very large. Interestingly, the first example of white dwarf was discovered in our backyard. I mentioned the star Sirius. which is only 9 light years away from us. And in 1844, the German astronomer Friedrich Bessel, whose name some of you may have heard because of his mathematical work, he noticed that the motion of Sirius in the sky is not in a straight line, but in an undulating curvy line. And he deduced that there must be a companion star which is massive but not seen easily, whose gravity is making the motion of Sirius in an undulating curvy line. And now we know that the companion Sirius has a companion. So this is seen in X-rays, for example, and this is seen in optical Sirius and Sirius B. And now we know that the companion star is actually a white dwarf star. And we also know what is holding, what sort of physics is there, what sort of pressure is helping the matter in such a white dwarf star to hold up against the gravity. It turns out that electrons are very asocial. They don't want to mix up with others, and so they want to exclude others in their vicinity. So that we call it the exclusion principle of electrons. So that gives a pressure, and so electrons try to exclude others from their neighborhood, and that helps them to hold up against gravity. And as you know, Subramaniam Chandrasekhar, he found out the largest mass of a white dwarf star that can happen, because if the star has a mass, say, more than say 1.5 times that of the sun, then even the electron pressure will not be enough to hold against gravity, and so that's the maximum mass of a white dwarf star. And so all this was discovered, the first came from our backyard, from our neighborhood star, neighborhood. So let's turn our attention to massive stars. What happens in the case of massive stars? So in massive stars, because the gravity is stronger, the temperature can be much more than in the low mass stars. So they can cook up elements which are heavier than hydrogen. So in heavy stars, not only hydrogen but helium can burn, and then carbon, and then oxygen, etc. And then oxygen will burn. So slowly all the other elements which are heavier than hydrogen are going to be produced in thermonuclear reactions in massive stars and slowly accumulate there. So what happens, it acquires a shell-like configuration where the lightest element, the hydrogen, is in the outermost periphery, and slowly the heavier and heavier elements are going to be produced there and accumulated there. Now this process stops when the core forms iron, because iron is the most stable nuclei. You cannot fuse two iron nuclei to form another heavier nuclei and still get energy out of this. To do this, you have to give energy, because iron is it's a very stable nuclei. Right? So the energy generation process stops when the core produces iron, and once that happens, basically energy generation stops again. Right? So as you know, what's going to happen is stars collapses, right? Because gravity wins again, because there is no energy production anymore. But it's a massive star. When it collapses, it's like, if you imagine IPL going on in Chinnaswamy Stadium, and suddenly, and there's a huge line for people to get tickets, and then suddenly say they run out of tickets and the ticket counter closes, and so there's going to be stampede to go towards the ticket counter. But people who still don't know that there is the problem there, they are going to come towards, and they're going to feel a pressure outward pressure from people, because of people who are already gathered there, right? So in a massive star, same thing happens. Energy generation stops. The star is trying to collapse, but there will be a pressure, outward pressure, and such a huge pressure basically destroys the star, shatters the whole star, and throws up everything that has been accumulated so far into space. Right? We call this a supernova explosion. Because of the supernova explosion, so all this material are going to be thrown out in space, and during the explosion, because of the heat of the explosion, some elements which are heavier than iron are going to be produced, like nickel, lead, and all the way to iridium. So that's very important. Please remember that. We'll come back to this point later on. So elements still iron in the periodic table are produced in the cores of the stars, all right, in the normal cores, and element beyond iron are produced during a supernova because of the heat of the explosion. Okay, so these explosions basically send shock waves through the neighboring region, clearing up the region and producing bubbles of hot gas. What happens to the center? So the center, the core shrinks because there is no energy production anymore, right? It shrinks further. It shrinks to the extent that even the atoms are squashed and the electrons are squashed with the protons to form neutrons. So the whole star becomes a sea of neutrons. So we call it neutron star, right? And because it has come, so as typical mass, solar mass star would have the size of a city like Bengaluru, like 10 kilometers across, right? So it's going to be very, very dense. And during this contraction, what happens? The magnetic field also is amplified. So huge magnetic field, and it also starts to spin very fast because, as you know, the conservation of angular momentum, like the ballet dancer's example, you know, if you start spinning and if I contract your the hand, then people are going to spin very fast. So these cores, the neutron stars, have huge magnetic field. They spin very fast, and because of this magnetic field, there is radiation emitted by them called the synchrotron radiation, mostly seen in radio, and along the magnetic field. So magnetic field is like a bar magnet, like a dipole magnetic field, and towards the pole there is a radiation coming out from these two poles, and if the magnetic field happens to be oriented at an angle with the rotation axis, then the radiation is going to come towards you. For example, you are seeing this pulsar, so we call it a pulsar. If you are going to see this neutron star spinning, and from your vantage point, if the magnetic field sweeps out in the field of view, and you are going to see this radiation and pulses, so we call them pulsars. And so they were discovered in late 1960s by Anthony Hewish and Jocelyn Bell, for which Anthony Hewish got the Nobel Prize. So this happens during supernova of massive stars, right? So one of the supernova example is from 1054 AD. So this is called the Crab Nebula. This is what it looks like now, but it exploded about 1,000 years ago. And it was noted by the Chinese astronomers as a guest star because suddenly a star became bright in the sky, and they noted it, and it was there for a few days, maybe a week, after which it basically dimmed away, and this is what it looks like now. So in the center of it there is a pulsar. Okay, so the core of the star which exploded has become a pulsar, and so our neighborhood also has a supernova remnant. So for example, this when the star is destroyed, it sends all this accumulated material inside the star and throws up in space. And the Vela, in the Vela constellation, you can see these clouds which are nothing but basically the debris of a stellar explosion. And coming back to our schematic diagram, this is the Vela supernova remnant. It's very near the sun, right? So this is an example of, so there must have been a supernova very close to us some time ago, which threw up all this material in space and created this region of supernova remnant, which looks like this. Okay. There is also a pulsar in our neighborhood, a very freak object. We call it Geminga, and it's the result of a supernova, and it's seen in the constellation of Gemini, which is why it's called Geminga. It's mostly seen in X-rays, and its pulsar properties have only been discovered very recently, and there's a lot of it's a topic of research. So it looks like our neighborhood has had supernova, and as I have told you earlier that supernova explosions clear out spaces and creates bubbles of hot gas region. And since I have mentioned this pulsar called Geminga, you are probably wondering whether the Geminga is the pulsar, the supernova explosion that caused Geminga is the reason why there is a super bubble. But let's look at the yes. So this is super bubble again. This is our sun, and this is where Geminga is. It's about 450 light years from us, and astronomers actually believe that the supernova that produced Geminga, this pulsar, probably was the cause of the super bubble, this region. Now you're probably also thinking that, well, Geminga doesn't look like in the center of this super bubble, so how can it be connected? Now it turns out that during this explosion of the supernova, it's not completely symmetrical. There are slight asymmetry, and that can give kicks to the center, the cores of a few hundred kilometers per second. All right. So after the supernova explosion, the core can actually move very fast, and it's possible that Geminga pulsar has moved away from the original site of the pulsar of the supernova, and so it's not completely ruled out that Geminga was the original supernova happened somewhere in the center of the local bubble. But it probably takes more than one supernova to create a region like local bubble, and there are actually from Geminga, from the pulses, one can actually date how far back ago it was created, it was produced, and it looks like it was it formed only about 300,000 years ago. So 1/3, 0.3 million years ago, right? But there are instances of, there are some evidences that of other supernova in our backyard, and that's what I would like to talk about. How am I doing in time? So I would like to tell you about a mind-boggling discovery a few years ago. A few German scientists found a block of iron in 2004 at the bottom of the Pacific Ocean, and this iron is a special kind of iron. Its atomic weight is 60 and not 56, the normal iron. So it's an isotope of iron, and it's a radioactive isotope of iron. So this is a piece of iron that they discovered, and so you can see a coin. This is quite a large block actually. And interesting things think about this isotope, the iron 60, is that it is not found naturally. It's very difficult to produce it through any natural process, okay, except in supernova. Right. So in during a typical supernova, the total mass of iron 60 that is produced is about Earth's mass, whereas in other natural processes, the amount of iron 60 that you would produce is negligible. So if this is true, then it looks like this piece of iron actually is debris from a nearby supernova, basically ash, fiery ash that fell on Earth from a nearby supernova. Okay. Now one can talk about what other things can happen during a supernova. So one thing that the German scientists found out is that, so one can date this event by looking at the depth at which of the crust of the Earth's crust from which this block has been found. So this has been found in a layer of the Earth's crust called deep sea ferromanganese crust layer, and it's about 5 kilometers deep, and they estimate that this was formed around 3 million years ago. Okay. And from the size of the iron 60 block that they found, the scientists have estimated that the supernova couldn't have been further than say about 30 light years away. So that puts it right in the, very close to us in the local bubble. So 30 light years away, a supernova happened around 3 million years ago, right? And a debris basically fell on Earth, right? Now what else happened So 3 million years ago, our ancestors were looking. This is Australopithecus. So an artist's imagination, you know, suddenly a guest star, a star brightened up in their sky, right? Now one can also talk about what else could have happened apart from the debris falling on the Earth. Now supernova, during supernova, what happens? You also produce something called cosmic rays. The cosmic rays are basically very high energetic particles like protons, electrons, neutrons and other nuclei, which are energized by, which are basically in the interstellar gas, but energized by the shock wave of the supernova. And so supernova produces cosmic rays, and cosmic rays are rays basically coming from all over the galaxy towards and hitting the Earth atmosphere. That's how the cosmic rays were discovered, by sending balloons aboard, instruments aboard balloons and taking them high up in the atmosphere. And recently there has been an experiment. So it's possible that the cosmic rays, when they hit the atmosphere, and people have asked this question, whether they can have any effect on our atmosphere. And an interesting experiment has been carried out in CERN called CLOUD. CERN, as you know, has been in the news for Higgs boson discovery, and it has been turned on last month again. So that's one experiment was carried out called CLOUD to find out the effect of cosmic rays on Earth atmosphere. It is possible, and the preliminary results are showing that there is probably some effect, some significant effect of cosmic rays on nucleating clouds in the atmosphere. Now, it's not conclusive as yet, but if it is true that the cosmic rays can have some effects on the climate of the atmosphere, then it's possible that this supernova, which happened 3 million years ago, around 30 light years away from us, it could have had an effect on our atmosphere, the climate of our atmosphere 3 million years ago. And we do know that the climate of our Earth changed 3 million years ago. It did, because that the Africa, for example, became arid, and the dry savanna became prominent in Africa at that time, which forced the primates there at that time to get down from the trees and start walking on 2 feet. And you know, as you know, the evolution of our species had a marked change around 3 million years ago because of the climate change, because they had to be forced down from the trees. Lucy, the earliest skeleton that has been found, is about 3 million years old. And so, you know, I sometimes wonder when these Australopithecus people, when they saw this supernova in the sky 3 million years ago, what were their thoughts? You know, it probably changed the course of the evolution of our species. So that's where I would like to end. And the results are very controversial, very speculative, but I find this a very fantastic connection between our neighborhood stars and what has happened on Earth. You know, what happens in our backyard need not be very boring. Thank you.
So we thank Professor Biman Nath for a wonderful talk. So what he has in essence told is that whether it is the stellar neighborhood or your own neighborhood, it's very, very unpredictable. And just like our own neighbors who are very unpredictable and mysterious, and therefore they should be understood, in the same sense, the stellar neighborhood, because it's mysterious, it needs to be understood. And he has conveyed that sense of purpose as to why we have to understand the stellar neighborhood in detail. So thank you very much for a very simple manner in which you made a very complicated subject look very simple. Thank you very much, sir. And we also thank Messrs. Video Hut Productions, Ashok Chawla and Devu Chawla, who have taken the responsibility of videographing the whole session. And very shortly we will throw up the session for a few questions quickly, if you can permit us. Okay. And just before that, an announcement. On the 27th of June, we have a special program, a one-day workshop on radio astronomy. There will be a poster exhibition plus 2 guest lectures, the details of which will be have been put up on our website. So please do visit taralaya.org and get details about this program, and do come back for this program on the 27th of June. So now if you have some questions relevant to the topic that he spoke just now, so we will welcome that.